This is the first lesson from Chapter 8. Chapter 8 focuses on coordinate geometry, or the coordinate plane, or graph paper, essentially taking or reviewing everything that we've learned in previous chapters and sort of relearning it or looking at it through the lens of graph paper. A historical side note is that René Descartes, a French mathematician, developed graph paper, or the coordinate plane, also sometimes referred to as the Cartesian plane, named after him. So moving on to the first thing, which is the distance formula. Previously we had looked at distance between 2 points that were horizontal or on a ruler, but now we're going to apply it to the XY plane. And in order to find the distance, maybe we'll call it D, between these 2 points, we're going to have to draw on the legs of this right triangle. And we're going to have to find the ordered pair for point C in terms of the ordered pairs for A and B. So A, we'll say, is x1, y1, and B is x2, y2. Then we can say for C that C is at the same vertical position as point A, and it's at the same horizontal position as point B. We can call this distance here maybe E, so that we don't have other variables, and F. And we know that with Pythagorean Theorem, D squared equals E squared plus F squared. What we also can say is that this distance, which we called E temporarily, is also the difference between the x coordinates, and this distance, which we had called F for a minute, is the difference between the y coordinates. So we're going to take these values here, and we're going to plug them into Pythagorean Theorem, and we'll square root it in order to solve for D, otherwise known in the picture as AB. And we're not going to do a plus or minus because distance can't be negative. So we'll do x2 minus x1 squared plus y2 minus y1 squared. And there's our distance formula, which probably looks familiar from Algebra 1. One of the things to note is that these squares and this radical can't cancel because of this plus sign here. So we'll actually need to number crunch this stuff inside of the parentheses, simplify it all down, and then simplify with the radical. So we'll go down and we'll do a practice problem. We'll find the distance between these 2 points, otherwise known as PQ. We'll set up the distance formula. It doesn't matter which point I label x2, y2, but sometimes it's a good idea just to mark it on your paper. So we have 4 minus negative 2 squared plus 3 minus 1 squared. And I'm calling this point P, x1, y1. So we'll simplify following or obeying the rules of PEMDAS, order of operations. We just keep simplifying until we get our exact answer, which is 2 root 10. And then we take this idea and we start to apply it to geometric shapes that we've studied before. So it says the vertices of a quadrilateral are provided. Describe this quadrilateral as specifically as possible. One of the things that I like to do is just kind of double check where these points are on the Cartesian plane. It looks like A is in quadrant 3, and B is maybe, well, it definitely is on the y-axis. C is on the x-axis somewhere over here, and D is in quadrant 4. The reason I'm doing this is I just want to double check which points form the sides, or which segments form the sides, and which segments form the diagonals. So based on this, what I'm going to do is I'm just going to start calculating distances. And I'm going to start with the sides and see where that takes me. And if that doesn't tell me enough, then I might actually start finding the distances for the diagonals. I need to maybe erase this. There's my first distance. There's my second distance for my second side, so I can tell already that AB and BC are not equal. So I know that this is not a square. There's my third distance, which is CD, which is equal to BC. So I have adjacent sides that are equal. So I start to have an idea of what sort of shape I'm dealing with. And then my last one So what I can tell is that ABCD is a kite. It has adjacent sides congruent. It's probably a good time to mention that although we're studying coordinate geometry, and I've kind of prefaced all this with the idea of graphing things, if we were to graph these points and see that it resembled a kite, it wouldn't be enough to then state that it is definitely a kite. Even if our picture is to scale, we'd have to go back and use some algebra to verify that. So we're essentially doing a proof with numbers to verify what's happening in the picture. So that's why when I sketched my picture over here on the left, I didn't bother doing it on graph paper, because I still would have had to verify all of this with the numbers. Number 3. A circle has a radius of 5 and its center at the point O at 0, 0, the origin. So we'll just kind of sketch this. There's the origin. Here is where the radius would hit on the axes. And it says, first off, show that the point 3, 4, which is right here, maybe we'll call it P. Well, they do call it P, 3, 4. Part A, show that it lies on the circle. So we're going to do the distance formula. Call this O for PO with the origin, which is really easy. 3 minus 0 squared plus 4 minus 0 squared. And that makes perfect sense because it had stated that the radius was 5. 5 is the distance. from P to O, which correlates to the radius. So that means that everything's checking out. It's looking for at least 6 other points that lie on the circle. So what I should be able to do is map this point around the circle, like so. In addition, I could flip-flop the positions of the x and y coordinates, which would cause them to change positions under the radical. But when I actually squared them, I would just have 4 squared plus 3 squared, and then 16 plus 9, which would still give me the square root of 25. So changing these should give me points that also lie in the circle. And I'll do the same thing that I did before, change the signs and come up with all these other options. And I could also include the easy to identify points which are out on the axes, like so. And I think we've got a good start, more than 6 points. Let's go to the midpoint formula next. This is the next formula that you're going to need to know. We have these same 2 points that we used in the distance formula. We'll plot points. This is A at x1, y1. This will be B at x2, y2. And we want to find the middle, which is point M, let's say. So that means that these pieces need to be equal. So again, we'll sketch in a right triangle. Call this point C, x2, y1. And one of the things I'm going to notice is that M is going to have the same x coordinate as this point here, which is directly below it. So I have a nice right angle right there. And over here, something like that's going to happen with a horizontal line in this point right here. Maybe we'll call these points, we'll call this D and E. Well, E is the average, because it's halfway in between, of the x values, and it's going to have the same y value. D is going to have the same x value as both of the points above and below it, and will be the average of the y values, like so. So now I know what the ordered pair for M is. M is going to have, the sum of the x values divided by 2, and the y will be the same. Essentially, we're averaging the x's and the y's. Average x's and y's. So the midpoint formula, pretty simple, but do note that quite frequently we're subtracting things, like with the slope formula or the distance formula. With the midpoint formula, we're adding. So we'll add and divide by 2, add and divide by 2. Add the x's, add the y's. Pretty simple. Let's try another one, number 5. All right, pretty easy. Let's go to the next page. Let's look at one that deals with variables, which is going to cause our answer to have variables in it as well. So we'll add the x's, which are in terms of a, and we'll add the y's, which are just integer values. And there's our final answer in terms of a. That's as simplified as we can get. Be careful simplifying here that you, in a sense, distribute this 2 that's in the denominator, or divide it into each term in the numerator that's separated by a plus or a minus. Then we can do this backwards. You have to read the questions carefully because it looks like it's just a traditional midpoint formula, but in this case they actually give us the midpoint and an endpoint, and they want us to find the other endpoint. So I'm going to take these sort of as my answers after I do the midpoint formula on a more traditional problem like the one previously. And I'm going to set it equal to this x value plus the missing x value divided by 2. And I'll just clear this right away. And there's the first part of my answer. I need to look for the y, so I'll take the y, which is one of the endpoints, set up a variable for the other endpoints, y, coordinate, clear, and then we do need to put this back together. And I made a little mistake here. Let's fix this. This is -12. This is -9. There we go. So 6, -9. And it's pretty easy to check your answer because all you need to do at this point is go back and check that if you take the 2 endpoints and average the x's and the y's, you should get the midpoint which they gave you. I'm going to let you do 8, and that answer will be posted on Blackboard under the notes key. Let's go down to testing for collinearity. There's a couple different ways to do this. So let's say we have 3 points like it states P, Q, and R. There's some situations that can happen with P, Q, and R. There's actually essentially 2 situations. P, Q, and R, when we plot them on graph paper, could form a triangle. Something like that. The other option is it's either going to form some type of triangle or it's going to potentially form a collapsed triangle or a line or line segment. And so one way to test that points are collinear, again, you could graph it, but that's not going to be the official test. That would just maybe give you an idea that it is or isn't going to be collinear, but then you have to justify it or verify it with the distance formula. And so the distance formula states that PQ plus QR equals PR if and only if the points are collinear. If and only if, meaning we could read this forwards and backwards. So if the distances are equal, if the 2 smaller distances add up to be equal to the bigger distance, then this highlighted picture, all of the points being collinear, must be the situation that we're dealing with. So we'll attempt it on problem 9. We'll find all 3 distances. So we'll find the distance for EF. FG and the last pair, which is EG. Okay, and what I can see here, and I can simplify this one down, but it's not going to make a difference. I can also tell, first of all, that these are not going to be collinear, because the only way that these radicals are going to add up and equal maybe one of the other ones is if they have a common inside or a radicand. In order to check that they won't add up, I also need to be able to compare sort of the size of each one. This one's the smallest, this one's the middle, and this one's the biggest. And root 13 plus 7 is not going to be equal to root 90 or 3 rad 10 because I can't physically add these up. These should have, all of these should have the same radicand, which is this inner part. So that's not working. So that tells me that these are not collinear points. And then it says if the points are not collinear, classify the triangle by both its sides and its angle. So based on its sides, I can tell that it's scaling. Based on its angles, I'm going to plug this into Pythagorean Theorem. And it probably isn't going to be equal. I don't think this is going to be a right triangle, but I guess we'll find out. And I need to plug in the largest value here. I'll put some question marks there because I don't think this is going to check out. And this means that the hypotenuse is too big. So the triangle, the right angle, is opening up. So this tells me that my triangle is obtuse. That was a review of stuff from chapter 3. All right, moving on to some algebra review. And I might leave some of these for you to try. Again, all the answers will be under where the notes keys are. Some of these are going to be strange. And it also says we can use any algebraic technique we want, substitution or elimination. So on the first one, I noticed that these are both set equal to y. So I might set the other portion of the equation equal. And try and solve for x. And I get a strange statement which is false. This is never true, which means that I have parallel lines, meaning I have no solution. That's sort of redundant. No solution. There we go. And I can also tell right here that this is parallel lines because they have the same slope, but they have different b values. Let's go over here to number 11. Try another one. So this one looks like a good situation for substitution again, which is what I did in problem 10. I'm going to plug this in for y really carefully. So 12x minus 4 times the quantity 3x plus 4 equals negative 16. And you can see again, this is weird. And if you wanted to add 16 to both sides, you could. But either way you look at it, this is true. So there's infinite solutions. Or essentially any point on these lines will work as a solution. You have to pick a point that's on the line. You can't pick a point that's off of the line. Otherwise, it won't work. Let's look at an example involving the elimination method. So number 12, we'll try elimination method, and maybe we'll multiply the bottom equation by -2. And we'll keep the top equation just as it is. And our goal, or my goal in choosing to do this, is I'm going to get the y's to cancel. Well, the elimination method or the addition method or the subtraction method, whatever you want to call it, these cancel, these cancel. I'm left with 0 equals -10. I've got another one of those strange ones. I think actually 13 is not a strange one, but the first three that I just did were strange. I'm going to leave you 13 to try. Let's go to the next page. And we have 2 more problems, and I'm going to do the one that involves the decimal. With the decimal one, I think it's, and also with the fraction one, I think it's a good idea to clear, and I'm going to clear by the power of 10, which correlates to the most number of digits behind a decimal point. So there's only one digit at most behind a decimal point at a given time or in a given value here in the first equation. So I'm going to multiply by 10. And I'm going to change this to 24x minus 3y equals, don't forget to apply it to your constant, -30. The bottom equation, I'm going to multiply by -6. And I'm going to get the x's to cancel, and I'm going to solve for y. And I can't forget to take this value and plug it back in. And I can actually plug it into any 4 of these equations. I think it probably would be easiest to plug it into this one. And there are my 2, well, it's really, I guess, 2 answers, but it's really 1 because it's a point, which is where these 2 lines intersect. So there's the first lesson. We covered a little bit of review of algebra, systems of equations, the midpoint formula, and the distance formula.